we will move to another session where we will focus currently on the automotive cybersecurity industry. And in that sense, when we are talking about automotive cybersecurity, we want to go to one of the tier one companies providing cybersecurity solutions for the industry. And for that, I would like to introduce Mr. Shalabh Jain, where he is a senior researcher and scientist at the Bosch Research and Tech Center, where he is focusing on design, privacy enhancing technology and security into the automotive industry. One of the things that always is challenging where we are modern today with these modern cars, they really know everything about us, where we go, when we go, all of our habits becoming very connected. So, Mr. Jain, I would like very much to give the stage to you so you can open our eyes about privacy on the modern of the automotive industry. Please.
Thank you. And I hope I'm just opening eyes and not scaring anybody from this presentation. Let me hopefully, without technical difficulties, hopefully my screen should be visible now. Okay. So yeah, so as I've been introduced, I'm Shalabh Jain. I work with the security and privacy team in Bosch in Pittsburgh. And Bosch is one of those big companies which pretty much, you can associate with anything, and different people I meet associated with different products, right? But what most people probably here don't know is Bosch is actually the largest tier one supplier of automotive components in the world. And I'm here actually to present, the privacy and security challenges some of the security and privacy challenges that we face within the role of an automotive supplier, right? I think just looking at the breadth of this conference, it's pretty obvious that, security is a broad domain. We have different business units looking at different aspects of security. One of the flexibilities that we in corporate research get is we're able to, of course, look at the short-term problems, but also have the flexibility to look at a long-term view of the domain. So, and I'll be presenting some of the thoughts. So the thoughts that I present here are basically more of those long-term thoughts and not something that's available as products, immediately. So to start off, so of course, the work that the topics that I present here are, of course, pursued by a very distributed team within the corporate research department. Which is our team is based in the US, Germany, and of course here in Israel. We also collaborate with a lot of universities, in this context. So, in case you're not familiar with Bosch as a company, just, to give a 1-minute brief overview. So, Bosch is, of course, one of those big global megacorps, and, in context of research, we focus on 4 major domains: so mobility solutions, consumer goods, energy and building technologies, and industrial technology. And of course, the driving factor behind all of the research that's done in Bosch is research that really matters and has an impact on society, right? Of course, not all, of course, though our research is focused on these 4 core domains, the applications actually go much beyond. So, for example, if you see the Ingenuity helicopter on Mars, that has Bosch sensors which are used for the stability control system. SoundSea project from our Pittsburgh lab is as of this moment floating around on the International Space Station doing analytics of audio to find problems early on. We have solutions like Analytics solution, which basically is used for rapid testing of COVID-19, and of course autonomous vehicles, which is kind of our core area of work. So we are, as a company, so just looking at the research part, we are about 1,800 researchers spread over, 12 locations, and all across the globe. We just I'm not sure if this is visible or if yeah. So we published around 18. So for example, just as a metric, our core focus is future innovation, which of course is sort of illustrated through the number of IP filings that we tend to do. We work very actively with a lot of PhD students in our company, over 200 PhD students now. Actually, we're actively working with this. Right? So, of course, working in this big company, security and privacy becomes very interesting because we work on a broad range of domains, and the challenges are very specific to each domain. And today I'll be basically focusing on the privacy and security research within the mobility solutions part, right? And notice that I've sort of switched the privacy and security around, because I want to sort of emphasize on the privacy part, not so much on the security part today. So, if we look at security in the automotive domain, cars were always sort of thought of as a standalone mechanical components, right? And as electronics started getting added to cars, the core design goal of automotive was still safety, right? It was never security, because these were just standalone systems, right? But slowly, electronics started getting added to these systems. Connectivity interfaces started getting added to these systems, and essentially, these systems went from being these standalone devices or standalone systems to something that's connected on the internet. And that's when we started to get into this cat and mouse game of security. Right? If we look at just from a timeline point of view, so pre-2010 there was a very niche community of attackers who would do things like custom engine tuning, or some attacks on CAN bus, the internal network of the car, using media file parsing and things like that. What really started to actually get people's attention was in 2010 a lot of academic researchers published some papers which really highlighted the malicious potential in the automotive space, right? Of course, these attacks were still limited to, through local interfaces, so OBD access or Bluetooth or Wi-Fi. Over the next few years, of course, there were more tools that became available. The community of attackers grew. And eventually, what was sort of a turning point within the context of automotive security was in 2015, when this 2015-2016 timeframe, when this remote attack on Jeep was demonstrated at Black Hat. And what this actually did is it led to the first security-related recall in the automotive space, right? And that actually started drawing a lot of attention from the industry, from the regulators. And sort of a lot of momentum within the industry was created around this time frame, right? Of course, things kept progressing. There's new interfaces to exploit. If you turn on the news, there's a lot of funky stories of people, videos of people doing key fob exploits to steal a bunch of cars, or disabling key functions. So there's a lot of interfaces that have been exploited since then. The industry as such, has not been, it's actually been quite proactive, reasonably proactive, right? The problem, of course, with automotive industry is that you can't do something as simple as have a patch Tuesday for a car and, be done with it, right? So, the design times and the cycle times within the automotive industry are very large. So, of course, any efforts that happen, at Bosch or any other tier 1 OEM take a long time to actually come into the market. So the industry has actually been quite active. So, different companies have different levels of maturity in this. Just talking from Bosch's perspective, so, way back, for example, in 2011, we've had, large teams looking at individual ECU protection. So, for example, introducing things like automotive HSMs or hardware security modules or physically unsoluble function within cars, looking at methods to protect the integrity of new software and data, right? But of course, the problems here are challenging in a very different way, right? Because you can't do standard crypto on an 8-bit micro, or you can't really transmit crypto metadata when your bus has a 64-bit payload capacity. Right. Uh, so we've sort of, our research agenda from just a security standpoint has evolved, so more going towards in-vehicle networks. So, coming up with, for example, innovative key agreement solutions, or looking at intrusion detection systems, or, new methods to improve the integrity of packets in CAN, right? And of course, more towards present day. So, solutions for connected vehicles. So for example, I mentioned like the key fob exploits are becoming pretty popular. So things like how do you replace actually key fobs with smartphone-based keying systems, so things like perfectly keyless or car-to-car or V2X functions. But if you actually see the next generation, right? So cars are no longer going to be differentiated on the basis of hardware, right? So actually, moving forward, it's pretty clear that the domain of automotive is going to move more towards software-oriented domain, and the differentiation will actually come from the services that you're able to provide based on the data that you're able to collect. And pretty much every big OEM has made very public statements about, the desire to collect this data and utilize this data to better serve the customers, right? And if you see that, so along these lines, some of the more recent attacks have actually been along the direction of leakage of private data by exploiting vehicle services. So of course, from a research agenda point of view, what we actually want to, all that we are also investigating quite actively is actually improving the privacy of users and introducing privacy enhancing technologies. Now, over the past decade, I think the security problem has been pretty well understood, within the automotive domain. It's by no means solved, but I think it's pretty well understood, and there's a lot of parties who are working quite actively. But if you think of privacy, this has really not been explored in as, or it has not received the attention that it actually should receive. So I want to spend the next couple of minutes actually talking in this context and see what the open challenges are in this area. Right? So privacy in the automotive domain actually doesn't start just when doesn't start after transferring the vehicle ownership to a user, right? Privacy problems start before that. So even during the design phase, so actually a lot of the automotive system design has been moving from traditional hardware design to more virtual components-based design. And this brings a lot of problems of things like needing to protect business IP. So there's a lot of privacy challenges around this. If you look in context of autonomous vehicles, so again in the design phase, autonomous vehicles are to design machine learning, deep learning system, you need to collect a copious amount of data to tune machine learning pipelines, right? And of course, this data can contain a significant amount of PII. So of course, there's a lot of privacy problems associated with that data. During use, I think there have been some examples recently, that have sort of illustrated the amount of personal data that vehicles can collect. There's a lot of benefit and an unexplored potential in being able to utilize this personal data to offer more personalized services to the user. But of course, this is PII data, so there's a lot of, there's legal restrictions that prevent this data. And of course, when you take your actually car to a workshop, there is a surprising amount of analytics which happens at that point. So it's not just analytics of what is wrong with your vehicle, but there's also a lot of metadata that can be collected, which can be useful for workshops to, of course, improve their services, but also to improve the offerings to the customers, right? But there are a lot of legal constraints that prevent using this data, and also a lot of things like antitrust laws, which prevent effective use of this data, right? Looking into the details of this, right? So looking at the design phase. So if we look at the traditional automotive designs, of course, automotive has a very complex supply chain, right? And but traditional design was based on hardware components. All the testing was based on what's called hardware in the loop. So what is happening now is that there's a strong push to actually virtualize all the components that are utilized during the design phase, and to take the complete design cycle virtual or using virtual components. So all your micros would become virtual, all your data, all your plant models, all your bus networks, power networks, everything would become virtual, right? clearly this has an advantage because you can do very efficient design. So for example, you can have faster design cycles, you reduce hardware costs, you can do a lot better testing, your testing costs come down significantly. So there's a lot of advantage here. But of course, going from here to all software, all the problems that are associated with traditional software systems also get introduced here, right? So if you think of this system as as a bus system or as an automotive system, the way that the system actually is designed is more like this. So you have things like providers, different providers who contribute models, right? So of course, this is a very iterative process, but they contribute models to an integrator or an orchestrator. So this would be an OEM, this would be tier ones or tier two suppliers, and of course there's different tools that are involved. So for example, orchestrators can use tools like COSIM, which could be running on cloud platform to orchestrate the system and then eventually have distribute the system on a distributed infrastructure. Right now, anybody who has dealt with cloud systems can look at this picture and clearly see that if we do a risk analysis of this, this has a huge threat surface, right? And there's multiple reasons for that. So of course, outsourcing infrastructure creates, more points for adversarial entries, but also this system is not really a cooperative system. It's more of a coopetition scenario. So the entities who are actually providing models here or who are actually integrating models here are not just cooperating, they're also competing with each other pretty much a lot of times on the same domain, right? So to actually have effective collaboration, you need strong privacy guarantees to protect the IP, to protect the test data, to protect design methodology that's associated with this entire end-to-end cycle, right? So, and a lot of companies, so till now, this has pretty much been done by, NDAs and business processes, but a lot of companies have actually started asking for technical solutions to actually enforce this and guarantee this, right? So if you think, if I put on my researcher hat for a minute, if I think about the type of required protections for such a system, of course, for these artifacts, you need protection during transport, at rest, and most importantly, protection of these artifacts during use, right? So if we're talking about models or any data in here. So at a very high level, right? I mean, you can think of actually trying to design what you would actually want to do ideally is design these black boxes. And these black boxes could have good properties or should have good properties. So for example, anything that you should be able to do anything inside this black box. Whatever you do inside this black box should be protected from anybody outside. You should be able to get data securely into the black box and out of the black box, right? So in crypto domain, we know how to design these black boxes. I mean, the literature for this has existed for a very long time, but the real research challenge here becomes, how do you actually adopt this black box to something that can be used within the civil domain, right? So for example, just to mention some of the techniques to implement these black boxes, you can have things like homomorphic encryption, secure multi-party computation, right? But of course, these are computationally heavy, right? From a civil domain, so what we are actually looking at is things like secure hardware extensions, which are provided by things like secure hardware extensions like Intel SGX, which basically provide this isolation between the Intel secure world or the secure world and non-secure world, right? But of course, it's not just as simple as creating this black box which can support performance, but it's also a matter of integrating these black boxes within this design cycle, right? And that itself actually brings a lot of research challenges. So for example, making sure that you can use these keys, without losing too much performance with traditional tools like, for example, MATLAB or COSIM or any other simulator that companies use, it's not really trivial, and it's kind of an open research problem that we're actually actively working on. Moving on, if you look at, of course, from a design phase, from an autonomous driving system, so if you can think of this as an autonomous driving system, I mean, I think everybody's quite familiar with this. There's a lot of environment data, personal data that is collected, which is stored and processed, right? Now, Pittsburgh, where our lab is kind of a test bed for 4 autonomous driving companies. So every time I go and grab my lunch, I'm basically photographed by 4 different companies. So it's quite, I mean, if I have to go to a doctor tomorrow and, give a summary of my lunch preferences, probably the 4 companies' combined data would do a better job than me reciting the history. But in certain parts of the world, there are strong laws which actually prevent effective use of the data. So for example, if you're testing in Europe, you have legal requirements which come from GDPR, where of course you either need consent of the subjects, which in this scenario is very difficult to get or almost impossible to get, or you need a very strong lawful basis for processing PII data, right? And this basically means you have to demonstrate legitimate interest. So there is actually there's a strong need to have privacy guarantees which can enable processing this data, getting insights from this data, while still complying with legal requirements like GDPR. Right? So this is of course a challenge, and if we see from a required protections point of view, of course you need privacy enhancing technologies, but the big component here is also of course you need legal assessment to demonstrate that this privacy enhancing technologies that you utilize actually satisfy the law, right? And this has actually been an open area of debate for both within the legal community, the academic community for a very long time now. So what are we doing here? So if you look at this this pipeline, traditional pipelines, you have data acquisition, storage, training. What we're actually trying to do is to see if we can enhance the storage, so the data lakes that we have with some extensions, which would allow for privacy. And here we're trying to use things like multi-party computation to actually enable this, right? Of course, if you use privacy enhancing technologies here, you also need to introduce it in other parts, right? So, for example, then you would also need to have extensions to your training pipeline, which would also then again use multi-party computation and things like T's, right? But again, the problem here becomes optimization and performance, right? So, if you're using multi-party computation and trusted execution environments here, then you have actually not just the performance overhead here, but actually this impacts your transmission, labeling, and training, right? So you have performance overheads in all these phases. So you then also need to optimize or create similar extensions for these phases, which leads to a lot of overhead, right? And optimizing that overhead becomes a very interesting research challenge. Of course, from a training part, a lot of training is done on very specialized hardware. So coming up with hardware extensions which can support these privacy enhancing technologies. So, so for example, extending GPUs to or combining it with T's. These are actually pretty open research problems that nobody really has a good answer to, and we are still quite actively investigating within our lab. So moving on, so private data. I don't know if you've seen this graphic. So NHTSA, the National Highway Transport Safety Administration in the US, had published this graphic a couple of years ago, which sort of highlighted the private data that is collected in cars, right? And it's quite a lot of data. There's actually benefit to move this functionality remotely. So for example, you can have new business models like personalized services, predictive maintenance, personalized insurance models, right? There might be legal requirements, things like intrusion detection systems. But of course, this is PII data. So when we think of PII data, we basically think in terms of GPS coordinates, but there's actually a lot of indirect driving behavior, indirect PII data that can be collected by cars, which is actually currently actively collected by cars. So looking into this, okay, so I'll quickly go through the next just 2 more minutes and then I'll quickly wind up. So looking into this, so we are looking, so if you think of this as an architecture, the data goes to the cloud, which can do things. You can have things like the remote intrusion detection system, intrusion prevention systems. So we are actively looking at things like statistical disclosure control, tools like differential privacy to actually add some noise to this data so that you actually can maintain privacy while still using it. But of course, The research problem there is, things like statistical disclosure control tend to be very domain and very application specific. So coming up with general methods which allow you to use this data, for multiple use cases is actually very non-trivial, right? And we're quite actively working on this. From a workshop analytics point of view, so I'll quickly go over, just jump over this. So workshops actually can collect a lot of data, for improved sales potential, for upselling, cross-selling, and also a lot of component analysis and logistic optimization, right? But the problem is that this data again has PII and antitrust components, relevance, right? So there's laws which prevent analysis of this. What's done today is, so data is collected, data is aggregated. There's very limited capabilities that you can analysis that you can do because this data is very anonymized, right, and not very flexible. So what we're actually doing is, again, using the statistical disclosure control, and so first of all, extending this so that anonymization is not the only privacy enhancing technology that you use. So leveraging things like MPC and T's for this, and of course, analyzing the extension, the capability of analytics to utilize privacy enhancing technology as well. The challenge here is, of course, doing this so that the pipelines are scalable, so you can use things like Kubernetes or scalable cloud pipelines is not trivial, but something that we're actively working on. The one thing I want to highlight is that if anybody has worked with automotive industry, you'll see that automotive industries tend to be very closed in general. But one thing that we have realized is that within the domain of security, there's a big potential for cooperation. So there's actually a strong push to develop the fundamental technologies that I've highlighted, through public partnership or through open source. So, for example, the multi-party computation work, or all the technologies that we're working on that I've presented so far, we're actually planning to open source it either this year or going forward, through a Carbine stack. So anybody, other OEMs or startups, can actually start contributing to it and using it, right? And a lot of the work that is actually being done within these domains is actually done through public-private partnership. So, for example, two big government projects like Cryptex, which is a French-German project, or AgriGaia, which is a German project. So a lot of the work that's done is in public domain, right? And this is, of course, very beneficial for security, but also a very fundamental change in the way automotive or automotive suppliers view development of technology. Right? So that was pretty much for the overview. Again, that was a bit fast. If you have any questions, please do reach out to me through email or on Twitter. You can follow us on our research blog as well. And of course, if this work is interesting to you, we do have a lot of open positions for PhD students and full-time researchers.
Okay, excellent. So, Dr. Jain, I have a question for you. We have time just for one question. So the question from the audience is the following. The techniques that you are currently presenting are mainly basic focus on the research direction. Can you take down in your lab really a car, for example, a real car?
Sorry, I didn't get the last part of the question.
Part of the question is that your presentation is focusing on research topics and research direction. Can you really take down in your cybersecurity labs a real car? And they wrote here the name of the car, so I will say it. Can you take down a Tesla car, for example, and hack it really in reality?
So we're not allowed to, to attack, the companies that we collaborate with, right? But through academic partnerships, we have found vulnerabilities. We have disclosed vulnerabilities in the past, right? But the work that I've presented here is not so much from an attack point of view. So to answer your question, yes, that could be done. We don't do it, right? So that's not the goal of our lab. Our goal is more to actually develop technologies on the white hat side, so more on the defense side. And of course, in this case, more from the privacy side rather than the security side, right? We do have teams within Bosch who are actively looking at things like bugs, for our own products, but not so much competitors.
I understand. Okay, so thank you very much, Dr. Jain, for this presentation. Remind me to buy an old car which are a less digitized and less connected car, so at least I will know that I will come from point A to point B without being hacked by your hackers. So really looking forward to hear more about this down the road, because as new cars coming, electrical cars, the modernization, what we call the fifth generation of electrical car are on the road, traffic light becoming connected, smart cities becoming connected, everything become connected to connected. Your work will be continuously, so I'm sure you will have a lot of work on research in this domain.
There's really interesting times ahead. Yeah, I agree.
So I would like to present our next speakers. Thank you very much, Dr. Jain.